So for our last topic in differentiating polynomial functions, after we've figured out how to find all the derivatives, after we've figured out how to do a curve sketch, we're going to take it and get some applications going on. And usually we'd be doing finding local maximums and minimums and interpreting those. Before we get into these problems, we want to make sure we really have the things that derivatives tell us down. So if we have our function f of x and we are looking at the first derivative, what can we do with that? So, I mean, obviously I'm skipping the first point, which is if you can set f of x equal to 0, you can find those roots or x-intercepts wherever your function is crossing the x-axis. Now, if we go to the first derivative, x prime of x, did I say f prime of x? I think I said the same thing. If you set that equal to 0, what does that find? That finds where the slope of the function is equal to 0. And that happens when you have these local maximums, slope is 0 here, and local minimums. We can also find out where that first derivative is positive, and we know when it's positive, the graph is going up. We can find where that first derivative is negative, and we know where it's negative, the graph is going down. We can move on to the second derivative, f double prime of x, let's call it. And if we set that to 0, we find inflection points, which is where the graph turns from concave down to concave up or vice versa. So if we have some crazy Loch Ness Monster guy going here, our inflection points are approximately here, turning from concave down to concave up, here, 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 and that's it. And once again, if we find the second derivative of x and we see that it is positive, we know that we are concave up. And if we see that it is negative, we know that we are concave down. And just to really hammer it home, let's do one start to finish. Analyze and sketch. F of x is equal to this string of terms. So I don't know, because we didn't do polynomial divisions, how to find the roots of this equation. So I'm going to abandon that thing, but I'm going to move quickly to find the first derivative. And this one's pretty straightforward. You're just going to take each term and find the derivative. So we've done this a million times. We're going to get 6x squared minus 6x minus 72 and nothing for the 7. I want to find when this is 0, so I want to be able to do that. So I feel like factoring might be in play. I see that I can common factor first, take out a 6, leaving x squared minus x minus 12. Continuing on, factoring what is in the brackets, 6 onto x minus 4, x plus 3. The zeros of the right side. When is this true? If x is equal to 4 or negative 3. So what have I found? I know that I have maximums or minimums at the point x equals 4 and the point x equals when x is negative 3. Before I do anything with that, I'm just going to continue on and find the second derivative, looking at the first derivative and differentiating again. 6x squared becomes 12x, minus 6x becomes 6, and the negative 72 disappears. Once again, if I want to find the zeros, I see that to make 12x minus 6 equal to 0, that would happen when x is equal to 0.5 or 1/2. That's my inflection point, so that's fine. But I also can use this second derivative to figure out whether these 2 points, when x is 4 and x is negative 3, are maximums or minimums. So what I'm going to do, I'll just give it a little highlight so I know that's what's happening. I'm going to find the second derivative when x is 4. And that's going to be 12 times 4 minus 6. And all I'm going to write down, it's positive. If it is positive, that means the graph is concave up, so we have a minimum. And then I'm going to find x prime, second derivative at x equals -3. And I see that if I put that in, I would have 12 times -3 is -36 minus another 6, -42. All that to say it is negative. So at x equals -3, I have a maximum. And I can start to put this graph together with a very, very rough sketch. I'll make my axis. This will not be to scale. Put in my key x values, so I see that something is happening when x is -3. When x is 0.5, we have that of inflection. And when x is 4. And I have decided that when x is -3, we have a minimum. Nope, sorry, we have a maximum. It's like, whoa. So let's say it's doing something like this. We are having a point of inflection at 0.5, so that's when it changes. I kind of missed there. And then I need to get all the way over here and have my minimum at x equals 4. If you wanted to have these points more precisely, you could absolutely go back up to the original equation and insert all these x values into it. So you could find, say, f of 4. You could find f of -3. And you could find f of 0.5 and really pinpoint those down. And I think I actually have them written down. And I think -3 was 142. So it's very, very high. Obviously, I'm not to scale here. F of 4 was -201. And f of 0.5 was -29.5. Okay, so those are the exact points. And if you find curve sketching offensive, of course, you can always double check with Desmos or any kind of graphing software or calculator. So there we see our maximum at -3. We see our minimum at 4. And, you know, we could say that our point of inflection is somewhere here, over here rather, at 0.5. Okay, now we're ready to get on to the nitty-gritty. As we just saw, when the slope is 0, we're at a maximum or a minimum. And these are our local optimal values. So these are where the interesting things generally happen on a graph. So you can use these for revenue problems, find out when you're going to make the most money. You can use these for kind of surface area or volume problems where you're trying to minimize material or maximize volume. And you can do these for velocity problems as well to find a maximum or minimum velocity. The nicest problems to start with are when they give you a formula and you just have to find the derivative and use that. Okay, so let's look at this word problem. So we have a company where the employees are making circuit boards, and how many they can make N is modeled by an equation given here. And T is a number of years of experience an employee has in making those things. So what they're asking is how many years of experience does it take to achieve maximum productivity? So what are we looking for? We're looking for local maximums or minimums, which means we are looking for when the slope of the graph is 0, which means we're looking for when the derivative, the first derivative, is equal to 0. So let's take the equation and find the derivative. So we're going to do dn dt, or if you prefer, the first derivative like that. And here we go. So -0.05 t squared. We're going to take the t squared, move the 2 in front, and we're going to have 0.1 t. 3t, we change into a 3, and we drop the 5. So we know that we are going to have maximum productivity when this equation is equal to 0. Let's do a little rearranging. Divide both sides by -0.1 to isolate t, and we're going to end up with 30 equals t. So how many years does it take of experience does it take for this maximum productivity? 30 years. And at that point in time, what is the maximum number of circuit boards you can produce? Well, we're just going to find n of 30 And we sub that 30 into the equation for any t's. Remember, don't sub it into the derivative equation because that will just get you back to 0. And here we go. And when you do that, you're going to get 50. So after 30 years of experience, you can make, in a day, you can make, say, 50 circuit boards. Wow, that's pretty impressive, especially judging when you have 0 years experience, you can only make 5. Good improvement. Of course, not all questions are going to give you a formula. So I always call this level 2 when you have to make your own formula. So let's look at this one. Looks like we're maximizing area here and we're given like a length of fencing that we have. So we have to really draw this well. So we're going to build a rectangular pen. So pictures are your friends in these questions for sure. And we have it divided into 3 parts using 2 parallel partitions. So 3 parts. So we're going to put a partition here and a partition here. And I see that I have 3 parts. So we're using up fencing in the middle. And that's where it gets a little more complicated. So let's say the width of this rectangular pen is x. And I know these partitions are also going to be x long and x long and x long. So just by building the 2 outside widths and the partitions, I've used up 4x meters of fencing. So how much do I have left for the top and the bottom, or the 2 lengths of the fence? I had 1200, but I got to take away the 4x I used on the widths and the partitions. Okay, so I have 1200 minus 4x for both the top and the bottom. So if I wanted to know how much I have for either side, I can just split it in half because this is a rectangle, top and bottom are going to be equal, which means both the top and bottom will be 1200 divided by 2 minus 4x divided by 2, 600 minus 2x. So suddenly, just looking at the pen, I can get an equation for the area because I know area of a rectangle is length times width. And I see that my width is x and my length is 600 minus 2x. I'm going to distribute that x to make my life easier when I find the derivative. 600x minus 2x squared. Okay, so I want to find a max area. I want to find a local maximum for this formula. So I am going to take the derivative of this equation. (600x) turns into 600. Negative 2x squared turns into negative 4x. Okay, when the derivative is equal to 0, the slope of the graph is 0, that's when I have my maximums and minimums happening. So I need to solve this equation comme ça. You're going to move the 600 over, divide both sides by negative 4, and going to end up with x equals 150 meters. So I know that the dimension along the x dimension, the width of it is 150 meters. And if I wanted the length, 600 minus 2 times 150, I'll actually write it down, 300 meters will be the length. So those are the dimensions of this pen. Now, what did they ask for? That will give you the max possible area. So the dimensions are great. Make sure you answer the question. They want the maximum area. So here we go. A max is going to be the dimensions we just found, 150 width times 300 length, and that gives me 45,000 meters squared. Level 3, you're going to need a couple of formulas because you're going to have one formula that solves and another formula you're going to use to isolate an additional variable so that you can go into solving that main formula with only one variable. So let's look at this one. We have a capacitor and it's going into a cylindrical container with a certain volume. So I know the volume, let's really quickly write down a couple of formulas, of a cylinder is pi, a number, r squared h. So my problem here is I have r and h. I have two variables. And the other thing, when they say dimensions of the container requiring the least amount of material, they're talking surface area. And the formula for surface area of a cylinder is the area of the top and bottom, the caps, or the ends of the soup can, which will be 2 pi r squares, and then the area of the label or the wrap around the sides, which is just the circumference, 2 pi r times the height. These are lookup formulas. They're pretty standard. They'll be on your formula sheet as well. I have a volume given to me, so that's not going to be my main formula. That's going to be my formula that I use to isolate a variable. Which variable I'm going to isolate? H. It's less common. It's only over in this one. So I'm going to isolate H in the volume formula because I know that I want it to be 2,000 centimeters squared. So pi r squared h, which means that h is going to be equal to pi r squared over, oh, bad, thinking ahead, 2,000 over pi r squared, better. Okay, so now I'm going to take this h that I just isolated and put it into the surface area formula for that h. It's all about my masterful use of the English language here. 2 pi r squared plus 2 pi r onto 2,000 over pi r squared. Let's clean this up a little bit and set it up for differentiation. Surface area is equal to 2 pi r squared plus 4,000, because 2 times 2,000. I'm going to cancel. I have a pi in the top and the bottom, and I can cancel this r, and I can just make this a single r in the denominator of the fraction, which I want to write as r to the power of -1. And that's just because I know it's easier for finding a derivative. Okay, I want to minimize the surface area. So I'm solving once again. I want to find the derivative, set it to 0, and find what radius creates that situation. Okay, so here we go. dSA or SA prime relative to the radius. 2 pi is just a number. So I differentiate the first term and get 4 pi r. I differentiate the second term. I get minus 4,000 r to the -2, which I'm going to write as 4 pi r minus 4,000 over r squared. Okay, this is a little messy. I want to kind of make it so I can easily solve this equation. 0 is equal to 4 pi r minus 4,000 over r squared. So what I think I'm going to do is use r squared as a common denominator and put all the terms also over r squared so I can combine them. Okay, so basically if I want to create that on the 0 side, we know where this is going. I'm just going to give you one that's long just in case you've forgotten how to do this. And then we're going to multiply in r squared to the first part. Okay, and at this point you can just kind of drop these when they're all the same. This is the beauty of the 0, and we're just going to get 4 pi r cubed minus 4,000. Here we go. 4,000 goes to the left side. R cubed is going to be equal to 4,000 divided by 4 pi. I do that math on my calculator, and I'm going to get r, when I find the cube root of 4,000 over 4 pi, is equal to 6.83 centimeters. Okay, I've found a radius. What else do I need to do? The question wants the dimension. So I found the radius. Now I have to go back over to this formula and find a height. And that should give me 13.66 centimeters. And you'll notice that the height is pretty much, and I'm just going to check this on my calculator as I talk, pretty much exactly double the radius, because that is your optimal cylinder size. If you have a cylinder where the height is double the radius, or I guess you could say the height is equal to the diameter, that's an ideal shape. These questions get really, really fun, really, really challenging. So I'll just show you one hardcore one. I don't expect maybe you would have to do this for me, but it's fun to think we could. So let's take, hopefully we know or remember a few things about electric circuits. So we see the sum of two resistors in series is 32. So let's call them R1 and R2 is 32 ohms. So what does that tell me? If I make R1 equal to X, then R2, in order to get that sum, must be 32 minus X. So going back to some old school things. So that's one thing. I've used a formula for series circuits to define these as with a single variable. All right, now what is their resistance if they have the maximum possible resistance in parallel? Parallel has a very different and very terrible formula. 1 over the total resistance is equal to the reciprocal of the first resistor plus the reciprocal of the second resistor. So if we take what we know, we have 1 over X plus 1 over 32 minus X. I would like to simplify this right side into a single fraction using an LCD. There's different ways to go about this. I think I'm going to do it this way. So I know that looking at the two denominators, my lowest common denominator that they both go into is just the two of them multiplied together, which means that I have to multiply this by 32 minus X and the second one by X in order to make them both over that. So at this point, I have 1 over RT is equal to 32 minus X plus X. And this is just me combining the two things. And I should have written in, actually, I should make this a little clearer by acknowledging that I'm also doing it on the denominator. And that's going to be over X onto 32 minus X. So far, so good. Clean it up a little more. And I see that the X's will cancel on the top. That's great. 32X minus X squared. Okay, that's 1 over RT. The problem is I'm not interested in solving for 1 over RT. If 1 over RT, the reciprocal of the total resistance, is 32 over 32X minus X squared, that means RT is reciprocal of the right side. Okay, we've gotten to the point where we're ready to go. Brutal. Okay, so we are going to find dRT with respect to X, or RT prime, and we are going to end up with 32 minus 2X over 32. When is that equal to 0? Well, if we cross multiply, we drop that, so we have 0 equals 32 minus 2X equals 2 onto 16 minus X, or you could have just done it straight up. So if X is equal to 16, that's when the derivative is equal to 0. The equation of the derivative is equal to 0. So what are the resistances? Well, let's say R1 is 16 and R2 is 32 minus 16, also 16. So there you go. If you want to have the maximum possible resistance of two in parallel, you want them to have the same. That's a challenging one. So with these problems, there's always a general, same approach. So hopefully you get a formula. If you do not, start drawing pictures and start listing your variables. Find out what you want to optimize, your y, like your area or your volume or your revenue, and then find the independent variable x. And then you're going to take any other extra variables and find different formulas like we did with the volume and surface area to express them in terms of that independent variable. Like when we take h and we made it into, 2000 over pi r squared. Once you get only one variable, you can differentiate. Once you've differentiated, take that derivative, set it to 0, and find what x is, what makes that true. Then go back, reread the question, and make sure you give me the answer that I'm actually looking for. It's challenging. We're going to do tons and tons of class practice problems. It can be kind of fun too.